What kind of incentive do you do?
Hey, how are you? Good.
My last. Ah,
You
wow.
wanna stay?
That's nice. That's nice.
If you want to stay, just saying. Last one? Last one?
Yes, I have a seminar on Wednesdays.
Congratulations. It's my last one.
Enjoy.
Thank you. You're probably a better person to teach that than I, but
I'm gonna go away before you. No, I don't think so. But it's for the PhD or the
It's
master?
both. It's
both. Ah, nice. Okay.
I have looked. At the end, I wrote lots of comments, including
I
on
finished with the paper on
embarrassing.
cool cities.
My paper. I don't remember.
Ah, yeah, I can. You have too many.
Oh, look what I did at the end. No? What is it?
Oh wow, I see. Crazy. Huh. Fun. No, I finished with the paper by Han and Stefan Ebrick on the cities, the cool cities, the trees coverage.
Yeah.
Very cool. I finished with that now.
Really?
Yeah. Yeah, but
I'll see you tomorrow. You're coming for there is a Christmas.
yeah, for sure. That's was fun.
Yeah. I'll come. I'll see you tomorrow then. All right. Let's make a start. So before I actually start today's lecture, this is our final lecture together. This is the last week of term. So that's very exciting. We learned a lot. We're going to do we're going to summarize everything later. But I just want to mention that, right. So a few things. So first of all, in terms of the seminars this week, so there is one seminar group that had to move from 12 o'clock to 3 o'clock because it's my fault. There is a speaker that I invited that come to give a talk, and they have to leave afterwards, coming from the US, and I invited them. So it's going to be a bit rude if I'm not going to be around. So we just have to change that a bit. So I'm sorry. In terms of what you need to do for the seminar is to read one paper. There are two papers that you were, according to the reading list, that you were supposed to read. One of them is a review paper. We're going to discuss a lot about that today. The other one is a paper by Manuel Linsenmeyer, Ben Groom, and myself, which is called Some Like It Cold. We're going to discuss this paper in the seminar. The other thing that we're going to do in the seminar, we're going to do that in the beginning. Then we're going to talk about exam preparation, which doesn't require a lot of time. I'm just going to tell you a bit more about the structure of the exam and what is expected from you, and answer any question that you might have. Right? So we're going to do both of these things in the seminar on Wednesday. And then the last thing, because I had a few questions about which papers are examinable, because we cover a lot of paper both in the lectures and in the seminar, and the answer to that is that I will produce a document that will be on Moodle that will specify all the papers that are examinable for my part of the course, which is this term. Okay? For next term, someone else is going to take care of that. All right? But for this term, I'm going to aggregate everything. Hopefully by the end of the week, you're going to get an email notification when it's done, I hope. But should be by the end of the week. It's going to be on Moodle, and all the papers that are examinable are going to be there. All right? Now, another thing, we're going to talk more about it on Wednesday, but just to say it already, the exam structure changed last year. So if you look at past exam papers on the LSE library, all papers before last year had a different structure in the sense that we used to have only one exam a year, the summer exam. We didn't have a winter exam, so it's slightly different. The exam questions are similar, but the structure is slightly different. I'm going to talk more about it on Wednesday, okay? But again, most of the time we're actually going to devote talking about the paper that I asked you to read. Okay, so today we're going to talk about spatial environmental economics with, question, of course, yeah. You should totally ignore that. Sorry, you asked me that before. I did ask Ruby. I have email evidence for that. And apparently what it was that, I think it was from last year, they scheduled something because they couldn't do something sometime. So it's kind of a legacy placement. But there is nothing related to GY426 on Thursday this week. Okay? Nothing. All right? Yes? All the papers that are examinable in January or for the econ students in the summer that were covered in this part of the course. So from week 1 to week 11. Okay? Everything. Okay? I also for the econ students that are taking the summer exam, I'm also going to talk about, it's also relevant for you because I talk about how your exam is going to look like and the type of question, what I expect from you, at least on my section. Okay? So it's going to be relevant for everyone. All right, so today we're going to talk about, any other questions? And thank you for those that fill in the surveys. That's great. All right. Today we're going to talk about spatial environmental economics. So this is the first time that we're doing this lecture. We just, when I say we, I mean I felt that it's kind of time to take this a bit more seriously. We already covered space when we talked about policy. So we assume that we know that. But we're going to talk a lot about other things that, how space essentially affect not just policy, but many other things, including evaluation and estimation. All right. So comments and feedback specifically for this lecture. If you want to give me what you like, what you didn't like, you can email me if you want. That's going to help me to potentially improve it for next year. I try to keep everything high level just to kind of, make it fun, but also extremely, I think, or relatively educational for you. But again, as always, if you have questions, feel free to ask. All right, so let's start with kind of the basic here. Environmental problems are not evenly spread across space. I assume that by now you already know that. Some cities, some regions around the world suffer a lot from air pollution. For example, some places do not at all, okay, or very little. Flood risk, heat stress, wildfire exposure also vary dramatically across locations. So it's not just about air pollution, although I talk a lot about air pollution because this is my main area of research. Not only, you're going to see it on Wednesday, but all of these things that I think you guys care about varies a lot across space. Think about the United States, for example. Think about wildfire, California, an obvious example, and you see much less of that, for example, in terms of wildfire, I think, in Miami or places like that in Florida, right? So you have this variation, not just in air pollution, but also in other environmental topics that you might be interested in. Economic activity also vary a lot across space. It's very uneven. People, firm, infrastructure cluster in particular regions and neighborhoods. People decide where to locate depends on economic activity, and economic activity depends on where people decide to reside, right? Historically, people used to reside next to water sources, even today, to be completely honest, or near natural resources. So all of these things are interconnected, and actually you can already see how that might have an impact on our estimation, because we don't know what caused what, okay? So that will make our life very, very complicated, right? And I'm going to show you some evidence across of that throughout today's lecture. Two big questions. There are more, but two big questions to kind of, I think, have at the back of your mind when we go through some of the evidence I'm going to show you today is, one, how do environmental forces shape where economic activity actually happen? Okay, and I already kind of mentioned a few things, where firms and people want to be across space and where economic activity would happen. We're going to talk a lot about agglomeration today, which is a shame because the person that was here before me, she's an urban economist, she's really the expert on that. I almost asked her to do this lecture instead of me, but she refused. Because we actually worked together on some stuff, but they talk a lot about agglomeration in the course that was here before you, so I'm going to spend some time on that. And then another big question is, how do spatial forces shape how bad environmental problems are, and who bears the cost? Okay, and there are like multiple questions that are hidden here, okay? And I'm going to try to unpack them as we go along. So kind of have this question at the back of your mind as we progress. Before I kind of move into some examples, I just want to clarify what do I mean by spatial here in this context. So spatial economics focus on the distribution of economic activities across location. You can think about it how, in terms of location, we can compare cities versus rural areas within a country. We're going to talk about that. Different neighborhoods within the same urban areas, within the same city. Regions within countries. You can think about different regions of the world. You have lots of kind of contacts here that, as you can see, space matters a lot. And the key objective in spatial economics is understanding location choice of households and firms. So why firms and households decide to locate in certain areas. Commuting and trade links. and also agglomeration and congestion. Okay, so this is kind of the key objective of spatial economics. We're going to try to use that here, how all of that is linked with the environment. Okay. To fix ideas, keep in mind the following sequence. First thing that we have here, we have an economic activity. Okay. Production, transport, energy use. Okay. All of that, all of this economic activity, we talked about it from week 1 or week 2 when we talk about, when we have this economic activity that we like, we get a byproduct, which is pollution. Actually, we said pollution back then, but then we made a distinction between pollution and emission. Remember that? So it's actually what economic activity creates is emission, right? And you can think about emission instead of ton of PM, NOx, CO2, whatever you have in mind, at a specific location, and how that emission translates to the ambient environment. We talked about the transfer coefficient, but this was a very simplified version of this link between emission and pollution. Okay? Because also, and we mentioned that I think either last week or the week before, what really matters is what people actually experience, where they live and work, so their exposure in many cases in terms of pollution concentration, flood, heat, all these kind of things that will matter for the last thing, which is damages, right? This is what we really kind of care about in terms of, in terms of the consequences, the externality that come from the emission. So in terms of damages, we're thinking about mortality, morbidity, productivity, property losses in terms of values, amenity losses, etc. All the things that we discussed last week in terms of air pollution, right? Now, the key thing in here that space matters at each stage, right? We said in the beginning where, economic activity varies across space. How emission travel also depends on space and some factors that we're going to discuss today. Also, the ambient environment where people are, but also in terms of, for example, their mode of transport and things like that. So what is their actual exposure? Indoor, outdoor, all of these things matters, and that obviously will also affect the damages. But damages will also vary because of other reasons, which we'll discuss today. So I will show you, for example, how the same kind of shock to the ambient environment can create very, very different damages across space. We can discuss why this is the case. Again, putting one more unit of PM 2.5 in the atmosphere might have very, very different effect in London versus Delhi, for example. Okay? Or being exposed to high or extreme temperature in rural India might be very different than being exposed to a heat wave or a high temperature in Delhi as well. Okay, so across countries, within countries, even within city, and we're going to talk about why that might be the case with some evidence. Okay. In fact, actually, now when I'm thinking about it a bit more, I can argue that damages go back and might affect economic activity. So we have a bit of a loop here. Right? Because that might have an impact on health, on labor productivity, etc., which in fact might have an impact on economic activity as well. So there is kind of a loop here. And you can already imagine all of these things are, connected. Some of them are extremely endogenous. How we can deal with all of that? The answer is that it's going to be extremely complicated, one. Two, if you think that by the end of this lecture you will know, kind of how to do that, and there is one best way to do that, the answer is that I don't think so, at least in my view. But I'm going to show you a few things that you might want to do in order to deal with some of these complexities, okay? But this is kind of really the frontier of research, I think, and there is a lot of things that we can do to make this better. So this is kind of, I think, there is lots of research opportunity here if you're interested. Okay, so this is kind of what we have in mind. Let's start by looking at some evidence. This is from the reading first, and then we're going to move to other papers that I didn't ask you to read. But this is straight from the review paper by Claire Balabuni here from LSE Econ and Joe Shapiro from Berkeley. These two maps here just show you the spatial variation in forest cover and deforestation. The left-hand side show you the global variation here. And what I think is kind of striking from this map here is that there is kind of the forest essentially around the globe is concentrated in two kind of regions, right? So in two kind of bands. So this band here, which I guess is kind of like Canada, then you have North Europe, Russia, like Siberia and things like that. And then basically here, which is what we're always talking about, right? This is why I also give the example, or they gave the example rather, on the right-hand side, which is what happened in Brazil, obviously the rainforest. But if you kind of deep dive a bit more into the right-hand side, into what's going on in Brazil, I think that, I mean, what you have here in green, you just have the forest that is present, and here you have in purple the forest losses, and you have the main cities, which are the red dots. And what you see that basically where we see loss of forest cover is actually in the areas that are kind of on the outskirts of the forest near to main cities, right? Where people are located, mainly also when you have the right transport link to kind of use the resource that we take from the forest and ship it to where you need to. Okay, and this is also where people need the income, right? So this is what we see here. So it's not just about the endowment, right, of the natural resource that we have, right? In this case, we think about forest, but you can think about some other stuff. It's also about where people are, which obviously also depends on that. That was my point before, but also about infrastructure and all these kind of different things. So that's kind of the first thing that I want to show you, okay? So again, forest losses, at least in Brazil, seems to me mainly concentrated around or near main cities, okay? Really where you have the transport infrastructure to move it across space, okay, in order to be able to sell it. And then you can also think about, okay, what happened first? Okay, there is a reverse causality issue again. Okay, did we build these roads there deliberately, or was it we decided to deforest in this location because we already had the infrastructure? So timing here going to play a significant role. So this is kind of the first thing that I want to see. The second thing, also from the review paper, we're going to move away from that in a few seconds, but I think the beginning of the review paper is absolutely fantastic. What you see here, you see the spatial variation in CO2 emission. On the left-hand side, again, you see global variation in CO2 emission. And what you see here, again, higher emissions, right? Look at that. This is the United States, you know, the usual suspect, Europe, China, India. This is regions with greater population density and also, on average, higher income in most cases, not in all cases. Okay? So we see that CO2 emission is highly correlated with those two factors. The other thing that you see here is that you know, you have a lot of kind of action going across transport links as well, right? Especially transport links between China, India, the US, and Europe. So this is all these things that you see here, okay? Across the oceans as well, okay? So you see, again, lots of the emission coming through trade links as well. Again, also going to have implication on how we estimate things, okay? Trade going to make a big, an important factor here as well. On the right-hand side, you have just within the United States, so how CO2 emission varies. And again, what do you see here? You see that you have a higher CO2 emission next to population density. So look at the East Coast, West Coast, pretty much across the board. When you have no population density or nearly no population density, you know, in the desert or Nevada and things like that, you hardly see any evidence for significant CO2 emission. Okay. and also that, to be honest, that's highly correlated with income as well, right? So that's the other thing that you want to see. This is really kind of, the East Coast. You have Chicago here, etc., and then California. Okay. Spatial variation in CO2 emission. Now we're going to zoom in Chicago. I mentioned Chicago in the first one. So this is kind of the Chicago area. This is Lake Michigan, I think that's called. Is that right? Thank you. I'm just checking if you're still awake. We're also in the geography department, so I have to make sure that you know what's going on. All right? You awake? Good. All right. So what we have here. So these are, again, maps of CO2 emission just for the Chicago area. Obviously, we have a finer spatial dimension here, spatial resolution, rather. What you see in panel A here on the left, you just see industrial emission. Okay, this is CO2 industrial emission. You see that it's concentrated here where you have both more population density but also more industry. If you look at total household carbon footprint, okay, what you see again that near basically downtown, well, where population density in the Chicago area is concentrated, you see high total household carbon footprint, okay? But then, and this is an interesting distinction, when you look at the mean household carbon footprint, so it's the average per household, we see the reverse picture here. What do I mean by that? The further you go from population center, so population center is here, right? This is kind of downtown Chicago, etc., and Hyde Park and all these places where people are in Chicago. If you go down here towards the suburb, you actually see that emission, CO2 emission per household, average CO2 emission per household is actually going up in the suburb. Anyone have an idea about why this is the case? Yeah. So this is absolutely, this is one of the explanations. You have a longer commute, right? That's definitely going to have an impact on CO2 emission. This kind of, if you think about from urban economics, you have the monocentric city model. This is basically what drives this point, that the further you are from the city center where you work, you have a longer commute, which is going to drive emission. This is the central part here. Yeah. Absolutely, right? Households stand because house prices, we talk about hedonic, right? It's further away. So in many cases, we see kind of a gradient in terms of price from city center. So the further you are away from city center, the price, again, it's not always the case, but there is some kind of evidence that there is a gradient here. So it's kind of go down. Therefore, they can afford bigger houses. Someone else? Yeah. Which also means that they have bigger. Yeah, this is what that's the definition of that. Yeah, no, but you're right. This is why we see this higher here. This is why it looks higher because basically we just have the scale. We just have more people. Absolutely. Anything else? I think yeah. Yeah, yeah, it could be actually. I need to think. That's yeah. I mean, yeah. No, no, no. I think it's a great point. I've never thought about that, but you might have this because some people. Yeah, I mean, especially in city centers, in many cases you get a concentration of less wealthy people. Yeah, absolutely. I've never thought about it. Yes. Yeah, no, that's a good point. I think that yeah, I think that's. But then you would expect that actually that people, if it's per household, then you're going to have more, right? Yeah. Yes. Yeah, but then they share the same stuff, right? So this is an empirical question actually, right? Because it can go either way, I think. Because now I share, like, if I share with more or less people, is that going to increase or decrease my carbon footprint? I'm not sure. My prior was what is the opposite of what you have in mind, right? Because if I'm just two people using one household, one like dwelling, compared to five, there are some kind of, I think, some saving that as five we will have, right? So that's kind of going.
I'm not sure how carbon footprint is being measured there, but maybe
This is per household.
I was just meaning like the consumption they have in each house and
Yeah, no, I think, yeah. I mean, could be, absolutely, yes.
Doesn't that, like, if you have more people in one household?
That's my, yeah.
Exactly, but then what you're talking about is per capita.
No, but what I'm saying here, I think this is here actually per, I mean, you can double check me, this is per household.
Exactly, but it would only be less per capita if you have more people in a household, then they will consume more. Even if they might be, sharing the heating and they would heat the same, they have other consumptions that would actually increase.
Oh, I see what you mean.
footprint.
Okay,
So
yeah,
per
I see what you mean.
capita, Yes,
Yeah.
it might be less.
No, fair
at the
point.
household level.
Totally, fair point. And everything that you, no, fair point, you're right. So, right. Everything that you mentioned is absolutely correct. Again, main thing, this is kind of how urban economists think about it, is about commuting. This is kind of the traditional way to think about it in terms of the economics modeling of that, because urban economists are the people that kind of mainly model that. It's also about, when you think about it, it's not just the distance, it's also the mode of transport. So for example, if you're in the suburb, you are most likely to have car or a second car even, etc. So that's going to increase your carbon footprint compared to if you are in a city, like places like, for example, well, here in Chicago, you can use public transport as well. Okay. Also, all the policy that we discussed, mostly policies around congestion and traffic is located in cities. We're going to talk about legislation. Okay. Anyway, this is kind of just to make the point that there is a spatial variation in CO2 emission. But actually, the point is kind of related to your point, I think, in a way. It's also going to matter a lot here what you decide to use for your analysis, right? So again, how you define some of the variables per household, per capita, consumption versus production, all of that, right? Here we're talking about production. This is total carbon footprint, but this is per household. So all of these things might also going to have an impact on your analysis. Okay. We can separate the determinants of environmental quality into three broad categories, okay? The first one is the scale of the output, okay? So how much output we actually create, okay? So let's say if we have more population density, do we see an increase in output? The answer is kind of yes. This is what we see, the evidence here, which just shows us the relationship between log population per square mile, essentially density, and log GDP. The second thing is the composition of the output, so dirtier versus cleaner industries are good, even within, well, I mean, when we compare cities versus rural area, this is what we see in panel B here, okay? So again, we have log population per square mile here, and here we have log mean emission rate. This is in terms of PM 2.5, okay? Again, we also see a very strong correlation between the two, okay? So basically what we see here is that counties that are more densely populated are also more polluted, okay? And this is coming because you just have more dirtier industry in urban areas in the United States compared to rural areas. So it's kind of relatively obvious, but it's kind of important to make the case here. So this is the composition. So what kind of industry is located across space? And the evidence here show that, at least in the United States, you have dirtier industry that are located in cities, okay, in urban areas, which is not surprising, right? The next one I think is very interesting when we talk about technique, okay, of production within industry. So here we're looking at within industry, and what I'm going to show you here is that is basically what I show you, similar to what I showed you before, so log mean emission rate, but here it's going to be per worker, not overall, okay? So this is emission per worker here, And then you see the complete opposite effect of what you saw before. Before it was a positive correlation, here you have a negative correlation. So what it says that basically within a given industry, denser areas have lower emission per worker. Okay, so the technique is better. They have potentially better technology or something like that, that basically generate lower emission per worker. Okay, within the same industry. This is again comparing essentially urban versus rural US. Okay, this is what's going on here. And what you see here, this is again local population per square mile, so measure of density and regulation. This is in relationship to the PM 2.5 regulation that we mentioned last week and the week before about the attainment, non-attainment. And basically what you see that, well, not surprising, urban areas are more likely to be non-attainment than rural areas. And that bit in here might explain some of what's going on in C as well, right? So you have more regulation, therefore firms, workers, etc., need to kind of be better in terms of how much they actually emit or how much they don't emit. Yeah.
So just that I get this correctly, that is within industry.
That's within industry.
There's no possibility that that's sorting.
This is within industry. Okay. So overall, what we get here, cities concentrate economic activity and dirtier industry. So we know that in cities you have more economic activity, but I think I'm not sure if everyone knew that. I didn't know that a few years ago. You know, you have, at least in the United States, you have more dirty industry near cities. But also, and this is kind of an interesting stuff that I just explained, they also adopt cleaner technologies and face tighter regulation. Okay? Which makes sense that they have tighter regulation because this is also where population density is, and this is what really matters in terms of health, right? Because we care about exposure, right? So the stakes are much, much higher. Yeah.
I have a question about what you said with like in the US that the dirtier companies allocated in more like dense populated areas. Because like wouldn't that mean that like if the areas were densely populated, then there's also more demand for like house prices, so then prices are higher. And given that like dirtier industries are often like pretty capital intensive, so they need a lot of land, it's not very optimal to be located in the areas where there's the most demand for land.
Right. So, so first of all, it depends on when, you know, and how. This is kind of what we discussed before. Like, basically, our firms decide where to locate based on. So, we're firms first, and then people decide to move towards the firm because of economic activity. So they're looking for jobs. So therefore, you know, why many people want to be in London? Well, obviously, it's a great city, and they want to come to study at LSE, but also because there are many employment opportunities. So maybe, you know, this population density is driven by location of industry, and but also firms need the workforce, right? So they also need to be next to they need people to employ in certain cases. So that's the case. And then the other point about land prices.
Yeah, because like if you're right next to where people live, then there's a lot of demand for land, so it will increase price. So like from a firm perspective.
Yeah, so it doesn't have to be that, right. So this is kind of transport kind of kicks in because you don't have to be directly near it, right? You just need to be connected to a certain way. And also there is a huge variation in land prices even within a city. Okay, so that's kind of, again, it's a very complicated set of affairs because lots of things moving simultaneously here. Okay, this is what makes analysis so complicated. So this is kind of, so that's what I said before, cities concentrate economic activity in dirty industry, but also adopt cleaner technologies and face tighter regulation. Whether a city is good or bad for the environment, it's an empirical question, right? Because we kind of said, well, emission per capita is actually going down, but overall we see higher emissions, so we're going to have to look at that. In fact, we're going to look at that today. So this is not a theoretical one, this is actually an empirical question because it can go which one, and you can think about different kind of environmental aspects that might suggest that, you know, cities are good for the environment, and in other cases, they are not, okay? I would argue that 10 years ago, everyone thought that cities are great for the environment, okay? This is what led us to write a paper that I will show you later today. Okay. Now we're going to move to something slightly different, but obviously very related. Typical spatial model, think about how goods, workers, and ID moves across space. What happened here in our context is that things are much more complicated. Why? Because the environment makes it more complex, right? So geophysical forces move the externality that we have. We talked about it. This is actually essentially the instrument that I discussed last week when we talked about crime and air pollution. I used the wind, right, as an instrument. This is what moves pollution across space. So that makes things much more complicated. And look, the wind doesn't care if we're in Westminster or Camden. It just moves pollution across space. In fact, it doesn't matter if you're in China, Japan, India, if you're in the United States, if you're in California or in New York. Pollution in California, from wildfire in California a few years ago reached all the way to New York City, right, through wind. Actually, it reached Europe as well. We, in many cases here in the United Kingdom, we get pollution from certain countries, which I'm not going to mention, in Europe. We also have some of you laughing, I guess you identify certain countries. We also get pollution from natural sources that, for example, we get some PM 2.5 coming all the way from the Sahara Desert. We get PM sometimes coming from Portugal, from fires, etc. Pollution is all correlated. By the way, China affects other countries in terms of their industrial pollution, but also they affected by other countries as well. Okay, in fact, China, with the war on pollution, made a tremendous improvement in air quality. It's just like almost unheard of. So, but again, there are some natural sources and other sources that affect their land as well. Okay. So emissions are local, but the ambient environment is shaped by wind pattern, atmospheric chemistry, river network, and ocean currents. We talk about a lot about air pollution, but if you think about water pollution, it depends. Are you upstream, downstream? You know, what happened upstream can obviously have effect on downstream. Yeah.
Taking account all of these environmental variables, how we can attribute certain areas in a typical quash experiment, like it's driven and controlled, if they are like very interconnected, therefore there's this separation, there's causality?
It's really hard. Yeah. That's the answer. So sometimes it's, for example, you know, when we saw the, last week, was it last week or 2 weeks ago? I don't even remember. When I show you the distance from the factory, and we know there is one factory, and we saw that you can actually show how the decay function of the pollution from the factory, and after, I think it was 1 mile, the paper by Reed Walker and others. So sometimes you can do that. I'm going to show evidence. There is some modeling that you can do to be able to see how pollution travels in space. But sometimes it's much more complicated. So, yeah, again, I said, things are very complicated. And this is the whole point. But I'm going to show you some evidence on how you potentially can do some of it today. Some of it you're going to have to trust other disciplines, because I don't think that, I mean, some economists are very good in doing all these models, dispersion models, etc. But in some cases, we have exposure scientists that are pretty good as well. So we can use some of their product in our analysis as well. So using our economic analysis, but some of the input will come from exposure scientists and things like that. Right, so this is kind of spatial variation in PM 2.5. And on the left-hand side, you see what happened globally here. You see that actually pollution concentration is very high here in kind of in Africa. Anyone knows why, by the way? Yeah. Yeah, absolutely. So I kind of mentioned it before in passing, right? You have obviously here and here lots of manufacturing. By the way, this is China. Some of the pollution in China, especially to the best of my understanding, by the way, I've never worked on China. Well, I have now a project there, but in the past. But lots of the pollution in kind of in the north come from Mongolia, etc. Right? So you have pollution coming from other countries as well. But over time, and the last decades or so, really the war on pollution really yields some significant improvement in air quality. It's fantastic in terms of what they manage to do. When they want to do something, they do it, and they do it well. It's just really incredible. So you see lots of variation there, but on average, what you do also see, even if you look at kind of a bit kind of more finer resolution, you see that again you have higher concentration of PM where you have higher density. Okay, so when you have population, etc. Yeah. Well, in here, I think that I think there are a few things, and again, I'm not an expert on China. That's what I said. I think 3 sentences ago. I think it depends on 3 things. One is absolutely wind patterns and things like that. Second is where population is and industry is, and I think that to be completely honest, is the combination of the two. So it's actually the intersection of where industry and population is and how this emission travel across space. Yes, yeah. So the land topography also there, even within a city, let me tell you that, even you have wind corridors within cities, so even the type of buildings, the height of the building, all of that going to have an impact on the distribution of pollution across space within a city. I mentioned this example so many times before. If you compare this pollution on one side of CKK, on the other side of CKK, you are very likely to get something different. That also affects how much you can trust pollution measurement. Yeah. I mean, what you? I mean, there is a difference. So you're talking about the UR River policy paper, 2014 PNAS paper that you talked in 428. Yeah. So yeah, I mean that was a change of policy. Yes. So in the north they rely on certain energy that change. I think that it changed here. So yeah, I mean there is different temperature that create differences in demand for certain things. Definitely in the winter months, etc. Look, there is a lot of things that might explain this variation. Okay? The point here I'm trying to say is kind of there is a lot of variation. Going back to your point before, how do you do that? How do you look at how pollution kind of move across space? So this is just an example from a paper that was published, I think, in JPAB by actually a former UCSB colleague, Kyle Mang. And what they do here is this example. This is just from LA. This is from a single factory. Okay, so they use this kind of high split model to show how particles kind of travel across space from one location. This is in relation to cap and trade program in California. So the paper is about something different, but we just took this one from the paper to kind of show how you potentially can do that if you want. Again, this is just one example. The point that the plume from one factory can move quite a lot within the state, and actually it can cross state borders as well. Okay, this is going into Nevada, etc. So yeah, so going back to the hedonic method, if you really take it seriously, you might want to think about whether you are downwind or upwind of a factory that's polluting and how that affects your health, and therefore that should be reflected in the property price. But this is kind of whether we have this information or not. That's a different story. That's why I keep saying that we need more information. Right, environmental damages also vary sharply across locations. This is what I kind of started the lecture with. I think the same temperature, the same level of pollution increase can generate very different health and economic consequences across regions. Okay? These reflect differences in baseline climate and environmental endowment. So maybe some parts are exposed to higher or lower level of pollution and or temperature. Access, this is really important, access to adaptive technologies and infrastructure. So, okay, so we are faced even the same level of temperature. Maybe we have difference in terms of access to technology or to infrastructure, which basically means that we will suffer differently from the shock. And 3, behavior and sectoral composition of local economies. Right? So what is the sectoral composition, how the local economy look like? That might also enable us essentially to adapt. okay, to temperature shock or something like that. So before we take a break, so wake up, okay, before we take a, do you want to take a break now or should I show you a cool paper before? What do you prefer? Cool paper? Who wants a cool paper before the break? All right. I love you guys. All right, let's do that. Let's do that. I'm going to miss that. All right, good. So this is a really cool paper. It's a bit old by Olivier Deschamps. He was hosting me last year at UCSB and Michael Greenstone. So they both did a PhD together at Princeton. And what they do here, they look at the relationship. This is a seminal paper in the climate econometrics kind of literature. They look at the relationship between temperature variation and mortality in the United States. Okay, so what they ask themselves, what are the impacts of extreme temperature in the United States on mortality? What are the impacts of extreme temperature on adaptation? So how people adapt to the extreme temperature over time. And based on this short-run adaptation only, what are the costs of extreme temperature of climate change, right? So they kind of, weather and climate change are two different things. I hope that by now you know that, but this is how they relate the two things together because, let me just show you how they do that. Right, so this is the annual distribution of daily mean temperature. This is kind of a cool figure that I have in the paper. What do we have here? So the yellow bars are just the averages across different temperature being about the number of days within within a certain mean temperature. So this is all in Fahrenheit, sorry. Well, it's not my paper, so I shouldn't be sorry. But let's look at here. This is more than 90. 90 is around 32 degrees Celsius. This is average temperature. This is not max temperature. Normally you see on your forecast max temperature. This is average, okay? So it's a lot. What you see that throughout 1968, in the years 68 to 2002, we had maybe 2 or 3 days a year with this kind of extreme temperature across the United States. And what you see with the red bars, this is basically the predicted change, okay, based on a certain model. They have different models in paper. This is one model that they use. And what you see from, this is basically the whole distribution. This is just an example for above 90 degrees, but you can see different temperature beings. But what you see, this kind of the point about the climate change and how they relate that is that, look, what's going to happen going forward, we're going to see many more days with extreme temperature. Actually, maybe the extreme is not going to be extreme anymore. All right, that's going to be the norm. But that's the point. And they want to try to figure out what are the consequences of that, because it turns out that all the bad things happen here and here, but mainly here, in terms of mortality, right? So it's when it's really, really hot. That's what they're trying to figure out. All right? So that's kind of the motivation. This is kind of the point of the paper. How they're going to do that? The beautiful thing is with weather, that weather is somewhat random within space. Right? What do I mean by that? So you can use a fixed effect to deal with most of the concern that you might have for identification. So if you look at, let's say, LA over time, sometimes LA has experienced very hot here, sometimes it's not very hot, and you can live off this variation over time. So you have within variation within space, right? So you compare LA with itself over time, and you see what happened. So on the left-hand side, you're going to have mortality in county C, time year T, and age group A. Why age group? Similar to the pollution. Remember that I told you when we talked about pollution that some age group are more sensitive to shocks and pollution. That's true also for temperature. And then on the right-hand side, the main thing that they care about is basically these bins that I showed you before. So this is going to be their treatment, okay? The outcome of, the treatment that they're going to look at. They look at the number of days within each temperature bin. All right? So basically, it would be like, what happened when you change, when you have an additional day, which is, let's say, 90 degree or above 90 degree compared to some reference group, which I think is around 20 to 22 degrees Celsius, all right, if I remember correctly. Something like that. And this is basically the result, right? So it's 50 to 60, that's the reference group. So basically that just tells you what's the effect of having one more day in temperature above 90 degrees Celsius instead of a day within this what they define as comfortable temperature. And what you get here, you get kind of a U-shaped relationship, okay, in which you get more mortality on each two ends of the distribution. Okay, when it's really hot, mainly, and also a bit when it's cold. Okay, so that's what's going on here. They also look at how people react to that, and the way that they do that, they look at residential energy consumption. So basically, how people can deal with the extreme heat, they can put the AC on or put the heating on. So they're going to see an increase in energy consumption. That's going to give them some evidence of adaptive behavior. And they see the same U-shaped relationship as well. Okay, so people try to protect themselves by using more energy, and this is the evidence for that. Again, does that mean that no one died? The answer is no, right? This is basically what I showed you here. Overall, this is a summary of the findings. We're going to take a break after that. 3% increase in annual mortality rate by the end of the century. In the last 35 years, US annual mortality rate has declined by about 1% per year, so that's quite substantial. They also found 11% increase in energy consumption, basically from air conditioning in response to hot day. And I think what's really cool in this paper is it's really highlighting individual willingness and ability to engage in costly adaptation in the United States. People are willing to pay, not to suffer. After the break, which is going to be a relatively short one, I'm sorry, it's going to be 8 minutes break. I'm going to show you how this relationship changed over time in another paper that they wrote in the JPE, and what we will see if we're going to do exactly the same exercise in India. And then we can see whether damages are the same across space or not, with the same temperature distribution, pretty much. Okay. So come back at 5:05, and we will talk about all of that. So you have actually 7 minutes. Sorry about that. Yeah.
A question. Yeah. Would this type of adaptation, like AC and heating, would create a loop or also make
Totally.
emissions?
That's a big concern.
Yeah.
So it depends. If you do not update the energy sector,
Okay.
such that the energy now would be coming from renewables, then you come into a loop.
But if these come from renewables are also affected by weather conditions, for example, like in South America, we had a very severe drought last year, and most of our energy matrix is 70% hydroelectric. Now it's gone.
Yeah, no.
So it's like more about the diversification of renewable sources.
Yeah, I mean, this is the problem with renewable sources in general, right? The sun is not always shining, whatever. You need batteries, you need all of that. Yeah, so you're going to talk all about that in the next term. I'm not going anywhere near that. But, yeah.
Oh,
But yeah, the loop point is spot on.
Okay. And when like Brazil, India, and other countries are increasing their GDP, it's getting worse.
That's the biggest issue. And I'm going to show you that today.
Very interesting. Thank you.
Yeah.
I just had a quick question. Is this like average across the country?
Yes.
Okay.
Yeah.
Like by population or just spatially?
So I think this
Okay.
is by county. This is the average county.
Okay.
Yeah,
Cool.
and county varies by population
Yeah.
and size,
That makes
right?
sense. Cool.
Yeah.
Nice.
Sorry.
All good. Thanks.
All right, you have another 30 seconds before I start. All right. All right. So let's continue. The truth is that I was worried that I might gonna run out of slides after 1 hour, and we barely started. So let's get going. All right. So this is what I said. Let me just remind you what they found here. This is kind of evidence for U-shaped relationship between both mortality and temperature, and also energy consumption and temperature. This is the United States. It looks significant. Looks pretty, etc. Well done. Then what they did in the follow-up paper, this is in 2011 AJ, right? That's an AJ paper? Yes, AJ applied. Then later on, what they were interested in, whether this relationship change over time. Why? Because of that. Because now maybe people, not now, over time maybe people have more capacity to adapt. Right? So in the following up paper with some other co-authors, they did exactly that. So they look at the mortality temperature relationship over time, and they did the same kind of bin temperature structure and the same kind of methodology. So fixed effect within county over time. So again, you don't compare Santa Barbara with, San Diego. You compare Santa Barbara with itself over time. Sometimes it's hotter, sometimes colder, etc. But then they look at kind of 3 different periods in time, right? So they look at 1910 to 1939, 1940 to 1969, and 1970 to 2004 that correspond to the blue, green, and red lines here. And what you see that over time, this relationship declined, right? So the effect of temperature, right, is actually lower in recent or relatively recent years, right? The recent data that they have compared to basically where the beginning of the data. So this is what you see here. Another way to look at that is through this figure here. So over time, this relationship between temperature and mortality declined in the United States. If you will ask Olivier what's going on here, he would say basically it's AC penetration in the United States over the last century. Basically, when people have ACs at home, the relationship goes towards 0. In fact, I think that he would argue that now it is 0. It's not detectable statistically. It's not that no one dies from that, but it's not statistically detectable. Okay? And this is coming from adaptation. Okay? Because actually you have more extreme events these days, right? But we just respond to that, at least in the United States, respond to that better. Now, some people on this paper, this is a paper that was published in JP in 2016, sorry. Some of the co-authors, including Olivier, Mike Deschênes, Michael Greenstone, and actually Robin Burgess from Econ here, and Dave Donaldson, that is PhD here, is now, I think, at MIT, was Robin's PhD student. They did exactly the same thing, but looking at India, okay? This is still a working paper. Still going on. I asked Olivier last year what's going on. So we're still working on that. They're improving it. It's been for 11 years, I think, a working paper. It takes a lot of time to publish stuff sometimes. Anyway, the point is that India is very different, as you know. I'm not going to go through all the statistics that I have in the paper. It's also irrelevant because it's old. This is just the latest edition. It's not the latest edition, but it's 2017 edition. But basically, this is how kind of the mean temperature distribution look like. Again, according to this model here, they predict that we're going to see many more extreme days, very hot days in India going forward, compared to what we had before. But this is already, I think, higher than what we see in the United States in number of hot days, but not meaningfully, I think, different. So, yeah, the distribution is not exactly the same, but it's. Again, the main point here is that we're gonna going forward, we're gonna see significant more days mainly in the right tail of the distribution. And what they do here, this is when they look at temperature and mortality in rural area, and they see this kind of, this is going. Oh, good. This is going back to Celsius here. So what they see that in very, very hot temperature, they don't really see many cold days like you see in the United States. So they don't really have anything, I think nothing really that meaningful here. But this is kind of what really matters here on the right tail of the distribution. When it's really hot, we see very, very hot. When we see very hot days, we see higher mortality. Okay? Now, what I want to show you next is basically what they did. They superimposed this thing here on the paper from the United States. Remember that in the US, we saw this U-shaped relationship between mortality and temperature? Let's see if they superimpose this on what we saw before. Look at that. Blue line is what happened in the US. This is the U-shaped relationship. It's all about the size of the coefficients, right? It looked almost flat compared to India. So what does that suggest to me is that even with being exposed to the same temperature bin, two different countries might have very, very different damages. And in fact, in the paper, which I don't think I have it here, no, I don't have it here, most of the effects coming from rural India. They have actually, I mean, what I showed here is just rural India. If you look at urban area in India, the effect is not as stark. So it's really about rural India that have this impact. Okay? So again, being subject to the same kind of shock might have different damages. Why the damages are different? Maybe this is your question, or you have something else to answer. Well, I don't know if it's compulsory. I mean, maybe in certain settings. I don't think it's. I mean, maybe some states and some places, yes. But I think at residential setting, I don't think it's compulsory to the best of my knowledge. Maybe in some institutional context, for example, in certain schools, in certain location, it is. By the way, this is true in many countries around the world, especially when you're exposed to high temperature. Definitely heating, etc. I mean, my son, we got a call last week that we have to take them back because the heating system collapsed. So yeah, this is London, right? We pay a lot for his childcare. So yeah, totally. But I think that kind of related to your point is that what might explain these significant differences is AC adoption. The United States is much higher. This is one story. Another story you might want to think is the structure of the economy that I mentioned, right? Specifically rural area, which may be more sensitive to to weather shocks. Right? It's more agriculture rather than industry. You work more outside compared to indoors work in cities and things like that. How much workers are exposed to the heat stress, and also what industry and how it affected. So you can imagine how crop yields might be more affected by extreme temperature compared to a worker in a factory in Delhi. Yeah. No, I mean, what is the cause of the change in the mortality temperature relationship? I think that, look, I don't know a paper on about the United Kingdom specifically. There is relatively less filtration. We have something around that in a paper that is not published yet. It's not even a working paper. We have the paper explaining that the variation across the United States, and we found that that's a significant contributor. It's really the AC penetration. So we have the variation across space there. But it's a bit problematic to attribute that causally because, again, adaptation of ACs across space is not random, right? So it's kind of heterogeneity, but whether you can say this is, that might explain, but there is lots of other things that potentially go in the background as well. Yes.
Obviously, like the US and India have very different healthcare systems and healthcare
Totally.
access. So how is it fully fair to say that like all of this is adaptation costs for India? Or
No, it's a combination. No, it's a combination of different things. So, and by the way, you can include healthcare provision as adaptation as well. So, like, look, people are going to potentially, right? This is one argument people can make. Look, we're going to have more sick people. We need to kind of adapt to that. We need to improve our healthcare system, right? So it depends on how you define adaptation.
I guess like my point is like even let's say climate change didn't exist, you would still want to improve the Indian healthcare system because it's
I don't argue against that. I think it's fair. But we're just looking at this relationship and this, yeah. In general, I want to improve any healthcare system if I can. Totally with you on this one. Same page. Right. So this is just to make the point about that. I'm not going to go through the summary, but this is if you look at the global variation in damages, this is a paper that came from, again, this picture comes from the review paper, but it's actually coming from another paper that was published, I think, in the QJE in 2022. That's right? Yes. By Tama Carlton and others. What you see on the left-hand side, you see the temperature anomalies in between 2000 and 2009. So you see that some places will get hotter and some places got hotter and compared to others. But also you see the mortality effect of climate change varies across space. Part of it would be AC adaptation. Part of it is different provision of healthcare, income, economy, lots of different things. Okay? I would argue that a significant part of it might be because of the ability to adapt. So I actually had lunch with Steven today, and I was talking to him about that, how crazy I am to do this lecture, because I was like, oh my God, I can't believe you're doing this lecture. It's a minefield, all right? But I was telling him about all of that, and he was like, look, I'm actually presenting a paper with a former ECC student that was sitting pretty much in this room 2 years ago, that pretty much does what you see here, like a global study, but here to look at mortality. What we did, we look at energy consumption. So he's actually just finished presenting this paper maybe an hour ago, something like that. So, so this is from their paper. It's not a paper yet. It just sent me slides. So this is Maureen Ludwig, which was a former ECC student 2 years ago. In fact, I met her. She was a pre-doc at Santa Barbara last year. I met her randomly at UCSB. I was like, do you remember? I was like, what are you doing here? We had a pizza party. And now she's doing a PhD at Berkeley. And that was her part of her thesis, right? And basically what you see here, this is the variation in electricity demand, and it's a really interesting story that they find here. This is different climate condition called mild and hot climate. And here what you see, this is income. So high income, mid income, and low income. And what you see that all the action in the variation in electricity, right, coming, right, only in is showing only in high income countries. You don't, you see a bit more, you see a bit in mid income, and but really nothing in low income countries. So basically it just shows you that high income country has the capacity to deal with extreme temperature. Okay? They still need to work on that. But this is very new. Okay? But it's pretty cool. I think it's pretty cool. And then they did this really cool stuff because we're in a geography, so we need to show some maps. Okay, so we like maps. So what they did here, they just do some projection on how electricity demand would look like mid-century. So basically, how did they do that? They estimate the electricity temperature response that I showed you before, then got some data on future temperature change, future income growth, and changes in electricity prices, and kind of basically show that across the globe, which I think is really good. This is not a published paper. This is not even a paper. This is just like some recent work. I mean, obviously she has a dissertation on that, but this is kind of literally came out in over lunch today as well. Okay, so what? Okay, I'm doing great with time. All right, so this is kind of what I show you. Again, what we're talking about here is how damages varies across space, even with the same shock. Okay, how the response, how we have different capacity to adapt because of a variety of different reasons. Okay, again, I don't know if that means that it's only AC that matters here. I agree with you. There are other things that are going on, but AC is probably a big story here. Or in general, by the way, energy. Okay, because we need ACs, but we also need to refrigerate our food and things like that. Okay, because otherwise we're going to have some other issues. Okay. Let's move a bit on and talk about agglomeration. Okay, so my urban colleagues love agglomeration. Okay, they're obsessed with agglomeration. What is that? They're kind of thinking when basically the point where people and firms come together, welfare are enhanced. Okay, basically we have more economic activity that is kind of spatially concentrated, and the reason why we get these benefits from agglomeration, I guess you can contribute that to 3 different broad reasons. This is kind of going back to a 2004 paper in the Handbook of Urban and Regional Economics. It's a really great paper, easy to read, to your point before, relatively easy to read, and kind of, even if you don't have sufficient background, so if you're interested in agglomeration, strongly suggest you to read that. Anyway, why does agglomeration happen? 3 things. One is sharing. Okay, this is kind of the first micro foundation. Yeah. Basically, when firms and people come together, for example, in cities, and that increase increase welfare and economic output. Okay, it's just the concentration of firms together. This is why we see Silicon Valley, for example. Okay, or why we see, or that might explain why you see higher economic performance of cities compared to other areas. Okay, and what drives that is the following 3 micro foundation. They argue in the paper from 2004, but this is kind of the normal way for urban economists to think about it. One is sharing. Okay, that's the first one. So firms share inputs. Right, they also share suppliers, infrastructure, and services. It's just easier because everything is located nearby, so it's cheaper for them to source input, to get suppliers in time, and all these kind of different things. Workers also benefit from that because they can access more employers, okay, and more profession. And also, importantly, cities share public infrastructure, okay, or public goods. So think about transport, think about London, the tube. It's fantastic to move people across space. Okay, so many people so quickly. Think about utilities. Think about where we are right now, university generating ideas, etc. We can all share that, okay, if we're all together, or relatively together in terms of concentration across space. So that's the first thing, sharing. The second thing is about matching. Okay, so how we match between workers and firms. So we're going to have better matching. Why? Because we just have a better labor market, more active labor market. So the matching of workers and firms is going to be improved. Okay, so you can really work in what you specialize. Think about where you're going to find your next job as an environmental economist. Is that going to be in rural Alabama? I don't think so. I love Alabama, by the way. But I don't think that this is where your next job opportunity will come from. Okay, I really do. I was there in June. I loved it. So matching, okay? So that's the second one. The third one, which is crucial as well, I love it the most, but it's probably, in my personal ranking, it's probably second after sharing, is learning. It's knowledge spillovers that you generate. Okay? This is from face-to-face interaction. So for after our career events, when we go to the pub and we talk and we come up with ideas, I'm obviously half joking. But you guys, the peer effect that you interact with people, with your neighbors, with people in London, etc., your classmates. And also firms can also get spillovers from other firms. Okay? And workers can get spillovers from other workers. Positive externality in this case. So these are often called the micro foundation of agglomeration. Okay? So this is why urban economists are obsessed with cities. They think this is good. Because we bring all of it together. This is why you want to cluster industry. This is why you want to cluster people together. Now, that's great, but we are not studying urban economics. We're studying environmental economics. So let's think about how all of that relates to the environment. Okay? By the way, I do study urban economics as well, but this is not the course for that. So, how agglomeration can benefit the environment? Well, one, pollution control exhibit increasing return from scale, right? So monitoring costs for the drinking water system, this is one example. Second, transport and housing may lead to lower emission. Think about that. If you're in the suburb, you are most likely to have a car. Maybe if you live in London, for example, I live in London, I don't need a car, right? So maybe my emission is gonna be lower. Adaptation infrastructure, right? So we can think about local good with fixed effect. Let's say in Miami, we need to buy some defense to prevent flooding, right? We have higher density. There is a fixed cost. We build it. You know, lots of people can benefit out from that. And also, it might be that reduced sprawl protect wildland. For example, think something like the London Greenbelt. There's a lot of debate whether the Greenbelt around London is good or bad. For housing prices, what does it actually protect? I'm not going to go into this rabbit hole, but it's something that I know that there's mixed views in my department about that. Is it really protect the environment, or does it just protect golf courses? Don't know. All right, we're not going to talk about that. But the point is that basically city can grow in two ways, out or up. There is a supply restriction because you have the green belt around London. That's the point. It's why I'm talking about it, because it affects house prices. That's what I care about. If you can't build out, you want to build up. But if you build up, that's great, but there are consequences. So therefore, there is some policies in place in London that prevent you from building too high. Okay, so all these restrictions, basically, they argue constrained supply, therefore demand is keep growing over the years, and this is what potentially explain the increase in property price, although property price seems to change direction in the last 12 months or so because of some other reasons. Okay, so this is how agglomeration can benefit the environment, but agglomeration can also increase environmental damages, right? So increase the marginal damage of local pollutants. A unit of air pollution has greater social costs when emitted in dense places because it affects more people. If I emit PM 2.5 in places that are not too many people, the damages are going to be relatively low, right? Compared to a place that has a lot. This logic obviously depends on whether we're talking about a global pollutant like CO2 or we're talking about local pollution like PM 2.5. And that kind of raised the question whether a city is good or bad for the environment. And as I was saying before, 10 years ago, many people were saying that cities are good for the environment. Why? Well, because the point is, and that's based on a paper, that in cities, emission per capita is lower. Okay, so in terms of CO2, there is a paper in the Journal of Urban Economics by Matt Kahn and another co-author. Sorry, Ed Glazer, I should have remembered his name. He's kind of the most famous urban economist in the world. That show that this is the case. It's a bit correlational, but there is some evidence for that in the JUE. So that's kind of the point here. Yes? Yeah, totally. That's exactly the point. So we don't know which, yeah. and the point is that we don't really know which direction it's going to place in terms of the different kind of overall effect. So we might going to expect to see, for example, in CO2 emission, it depends on how you think about it, but this is why it's an empirical question as well, where it's going to go up or down, but also in terms of comparing local pollution versus global pollution. And this is exactly what led us to write this paper. In fact, I was watching Ed Glazer, now I remember his name, God, I'm really sorry that I forgot his name, presenting a keynote in the university, in Tel Aviv University actually. I was visiting scholar there. And he was talking about how we need to build up, etc. And someone asked him in the crowd, if I remember correctly, it was someone from the central bank, why we don't build up. And his point was, his response was a bit provocative. He said, like, we need more pressure, so we need like a New York Times, front page headline of saying, if you're not going to build up, baby's going to die. And when he said it, I was like, I think I can write a paper that show exactly the opposite. And then after the lecture, I went to talk to him about it, and he was like, you should totally write this paper. So I did that. And basically what we're trying to do in this paper is to look at the effect of density, population density in the United States on pollution concentration. The point is that ex ante, right, we don't know which direction it's going to take, because we can think that it can go to different directions, right? So higher density might mean lower level of emission, which is kind of what I showed you before in the review paper in a way, right, by household. Because, for example, we don't drive or lots of different things. We use public transport or things like that. On the other hand, higher density also mean more, sorry, not in the other, it is in the other end, right? So in the other way. So higher density also mean more agglomeration and consumption, and therefore more activity, kind of going back to your point. But also higher density means that people are more concentrated together. Okay, so that's kind of go into the opposite direction. So if you take the first and the third one, what's going on here? It means that, look, it might be that each person in our city emit lower level of pollution, but overall, because what matters is exposure, because we just together, we are exposed to higher level of pollution concentration. So in terms of CO2 emission, that it doesn't matter where you live and where you emit, the point here doesn't really matter, and this is kind of the JE curve that I mentioned before. So what really matters is emission. But in terms of local pollution, what matters is exposure, and the fact that we all live near where emission is being created means that we potentially are exposed to a higher level of pollution. So it's kind of unclear which direction, what's the sign of the coefficient here, and then if you think that is, even if you think it is clear, which is definitely not, so environmental economists think that it's clear to one direction, which is they're right. Urban economists thought that it's going the other direction, and they were wrong. But even if you think that the point estimate is important for policy and to think about what's the optimal density in a city. Okay, because they think a lot about it in urban in terms of the amenities from agglomeration, but what's the cost as well in terms of, for example, the health cost from coming from pollution. Sorry, someone had a question. Yeah. We talked about it last week. It depends on the setting. Some it's linear, some it's not. That's another good point. Yeah, that's another good point. So it might be even underestimated here. So this is kind of what we were after here. By the way, a former ECC student was, for those of you that came to the PhD career event last week, Marguerite, remember her? Just finished Columbia PhD. She now at Northwestern postdoc, and she's going to join UC at Econ next year as an assistant professor. She was an RA on this paper when she did her MSc here. This is what she mentioned, if you remember in the talk. So this is what we did is together with Felipe Carozzi, the professor here, urban economist. So the objective is to get a reduced form estimate, and then also a parameter for environmental costing of density increase. It's more to policymakers. The challenges, look, the main challenge that we have, listen guys, so I remember, talking to Ed Glazer after the talk, and then I went straight into my office in the second floor in Tel Aviv, and then I called Felipe, because he's an urban economist, so like, Felipe, we need to write this paper. Density, I mean, how it's the most endogenous thing on earth, like, people sort on all sort of stuff. How are we going to do that? And he was like, look, I was at the NBR Summer Institute, I think it was. Then there are this group of people that came up with this instrument. We can totally use this instrument. And then we kind of start reading into that. We changed the instruments a bit. One of the PhD students we had in the department back then was actually an RA for those that wrote the other paper. So we had some inside knowledge. It was like a working paper, so it was all great. So that's kind of the main challenge. And then we have another challenge about measuring pollution. I already mentioned before that pollution is not, pollution monitors are not randomly located across space, so we use satellite data to deal with that. In terms of the instrument, and I'm not going to go into justifying each instrument, you can read the paper. I spent a lot of time justifying this instrument to the reviewers, but we were thinking about three different things. One is earthquake risk. Second, presence of aquifers, and three, soil drainage. All of these things might have an impact on the cost of building. All right, so that's the point, okay? So, and the shape of the building, whether you want to build really up or I was a bit surprised by the earthquake risk, but talks to some architecture that kind of explained to me why high-rise sometimes is better because it's just more flexible in terms of the shape and things like that. If you're interested, read the paper. We also have two other identification strategies there, which is one, use long lag instruments, so basically population density in the 19th century to instrument for now, which is something that's been used so many times. I don't know how good it is, but it's been used, and also long first difference as well. The problem with that we have less variation in a place like the United States over time, but you have that. And what we did within and between cities analysis, right? So we have a very, very fine grid, but what we really care in terms of policy is the between cities, but you can show some really cool stuff within city with like 4 or 5 million observation, which back then looked pretty impressive. Now, lots of people do that. So this is where we are. The good news is that, look, with density it's very hard. You can't randomly assign population. You can't do that. So nothing going to be perfect with population density. But what we think is encouraging that whatever we do with the instrument, and all, we have like essentially 4 different instruments, and we cut it in different ways, and we did everything. It's all point to the same direction. So we think it's very reassuring. But I don't know. All right. So what we found. So this is kind of a nice figure just to show basically how population density and PM concentration look like across space. So this is basically the distance from the population centroid inside cities in the United States. It's across the entire US. So the further you are from the city center, this is kind of the typical urban model. This is how it's going to look like, but this is just with data. This is real data. You see that the further you are from the city centroid, population density goes down and also pollution concentration goes down. All right? Lots of people say that might affect some racial disparities in the United States as well, okay, in more recent literature. And this is kind of preview of the results. Basically what we found that overall we have a positive relationship between population density and PM 2.5. Again, it's not clear that that's the case. This is the two-stage least square estimate. This is between city. We found that the elasticity is around 0.114. And in terms of exposure, it's basically increased by around 1 PM 2.5. Okay? So this is kind of in our preferred specification, which is here. This is the within city estimate. So we see larger effect in terms of the elasticity within city. Again, it's a much larger sample size, so you need to kind of, there are some things to worry about here. This is kind of the secondary point, but this is what we find in this case in here. Then what we want to do, we're trying to think about what's the health cost here. So we did kind of relatively back of the envelope calculation, but this is similar to what the US EPA does. We did it in 2 steps. So one, we kind of relate changes in pollution concentration with mortality concentration response function from the literature. So we took the estimate that we have about how population density move with the IV estimate, how population density move with pollution. And then we took 2 dose response function. What is that? Basically how changes in pollution affect mortality. The reason why we took 2, we took the lower bound and the upper bound estimate from what the US EPA used. So there are studies, the studies that report the lowest dose response function, and the study that report the highest one. So to have a range is where you're going to see a massive range. And then basically we use the value of statistical life, something that we discussed last week. Back then it was $7.4 million. And then we ask ourselves what would be the impact of doubling density in an average US county, just to make it more, more intuitive. So this is basically the equivalent of changing population density in Houston to the one of Chicago, if you want to think about it in this way. And basically we found that the mortality cost would range between 281 to 630 US dollar per capita. So that's what we did here, which is massive. Because if you think about, okay, so is denser places good for the environment? So no, then we go back to the JUE paper, think about the saving that we got from CO2 emission, take the social cost of carbon estimate, and see what's dominant. What's the the benefit and the cost of density? And we found that the cost is much higher. The health costs are much higher than the saving that you get from the lower CO2 emission that you reduce by having higher density. So that's what we did in this paper. All right. By the way, just kind of a point, we use, I think I mentioned it before, we use satellite data or reanalysis data. We just want to make sure that this is fine, so we just look at the correlation between the satellite data and EPA monitoring on the ground. We see that the correlation is 0.8. It's pretty good, at least in this part of the world and with this specific product that we use. All right, so also, I want to add some more stuff just before we kind of wrapping up. Economic regions are linked through the movement of goods, people, knowledge, and ideas. Okay, we talked about some of it before, but not all of that. Okay, people move in response to climate shocks, response to hurricanes, to respond to floods, etc., etc. Whether it's permanent or not, that's a big question, and that might affect estimation quite a bit. Good also move. We trade with each other. I mean, maybe now a bit less so, but hopefully we continue to trade. And knowledge and idea also move across space. You guys are from all different countries. You come in here, you're going to go back to your own countries, and we spread ideas as well, which is great. It's what we want to do. So all of these connection are also shared by transport costs, by infrastructure, and other friction. Think about how you moved here, how we move goods, how we move ideas. I mean, now we need to think about the internet and other methods to move things. I sound so old when I'm saying that, but you know what I mean. But traditionally, transport play, and still today, an important role for the environment, right? Directly create emission. I mean, think about how much CO2 emission is created by transports of goods. But it can also improve market access. We talked about daily commuting, how that affects. But commuting can also reduce exposure as well, right? So for example, you were talking about factories before, right? But I can, I can work in the factory and live far away from that because of transport. Right? So actually, neighborhoods or residential area can be far away from where polluting activity being happening, and this is due to good transport infrastructure. Right? So that's something that can actually reduce exposure as well. Again, I want to emphasize the point of ideas and technology. Knowledge flows shape environmental outcomes through the diffusion of clean technologies such as renewable energy and solar power. You're going to talk more about it in the next term. Spread of energy efficient production methods and innovation in agriculture that shift crop and practices towards greater heat and climate tolerance. And we see that really across the globe, how better technology really have significant improvement. Overall, environmental improvement in one region can greatly spread to other through learning and imitation, right? So what we learn here can affect what happened in other countries, or what happened in one country can affect other regions within the same country. Okay? Now, how much time do I have? All right, 10 minutes. No, I don't need 10 minutes. So far, we've seen the following. We've seen that emissions are spatially concentrated. Pollution travel across space. Environmental damages vary strongly across locations, the US, India, even within India, etc. And the paper by Stephen and Tamar Carlton, etc. And also, people and firms sought in response to environmental condition. I didn't show you that evidence for that because we have limited amount of time, but there are tons of papers that look at how environmental shock shifts people around and firms. So people try to get further away from these environmental shocks and locate in other places for a variety of reasons. Maybe, for example, they used to work in certain areas, certain industry that were deeply affected by a hurricane or something else. They need an employment because this industry is now destroyed, so they move somewhere else, right? Et cetera, et cetera, et cetera. The point is, and the complication is, that all these forces interact simultaneously. People move, something happens. If people move, maybe there is no economic activity somewhere else. There is not just a partial equilibrium effect. There is a general equilibrium effect. All right? You guys seem to be happy about that. Good? All right, just checking. So all of this stuff really kind of move, and we need to think about how it all interacts with each other. One thing that can help us to do that to a certain degree, and I'm not going to teach you how to do it at all, I'm just going to give you kind of very high-level description of what's going on here, is something called quantitative spatial model. Okay, I know that at least one person in the room is extremely interested in that. She's laughing in the back. Quantitative spatial model allows us to study this interaction jointly rather than one channel at a time. So what happened? Something happened here, then it affects other regions, people move, firms decide to locate, lots of things happen at the same time. Because of that, there is a loop, right? So then more emission there, then damages are different, healthcare change. The world is different, all right? So the reduced form estimate that we kind of liked using might not explain the entire story. It might explain some of the story, which, by the way, is super important. But if you're really interested in the entire story, you might going to miss some of these issues. Okay? So this is what you can use potentially. Quantitative spatial equilibrium model can combine household location choices. So how households decide to locate where, okay, their preferences. This is kind of one of the main things. The second main thing, I guess, I would argue, is firm location and production decision. So where firms decide to locate. Deeply care about transport, commuting, and trade across space. So how different regions in the world, are linked with trade. Trade is a key thing. There is a whole literature on trade in the environment, which is like really key here, right? Because you can think about, how we are, in London, are we more connected with New York or are we more connected with Sheffield? Okay, I don't know that. I don't know what's the answer. By the way, I love Sheffield. That's why I said that. But don't think that I'm being nasty to Sheffield. The point is that trade is important in here, and also environmental condition, environmental damages were also being modeled here. So they solve jointly for where people live, where firms produce, how goods, worker, and pollution move across location. Okay? Now, the way that it works, the model combines structural economic assumption. I try to be as diplomatic as I can here, and data to evaluate economy-wide responses. Okay? So they're going to put a lot of structure, they're going to do lots of modeling in order to estimate all these things and how they move together. How households decide on where to live, how firms decide to where to locate, how pollution moves across space, how we trade, all of that. They're going to have to put some structure. When I say to put some structure, I know I'm recorded, one way to think about it, they need to put some assumptions on that, around that. Okay? So you get a lot, so it sounds like really promising, which it is. This is kind of really lots of people working on that, which is great stuff. But obviously that's also come with some limitation because you're going to have to make some strong assumptions. Okay? And that's kind of the main point. Going back to, and I'm going to have a slide on the limitation here, but going back to climate damage heterogeneity, we saw that the same temperature increase causes very different damages. Adaptation, income, and sectoral structure matters enormously in the example that we mentioned before. Quantitative spatial model will allow us to, one, aggregate these heterogeneous local damages, endogenize migration and adaptation, because people will move in response to, for example, I mean, most likely, there is some evidence for that, changes in temperature and other changes in the climate, okay, and also in terms of pollution, and then compute the global welfare impact of climate change rather than just look at one country in isolation and treat, okay, everything else not going to be affected. But it might be affected through movement of people, through trade, through other things, through where people are, but also from where firms are as well. Okay? So this is kind of what they will enable us to do. So it allows us to move from what happens here in a specific country or specific city to what happened to the whole economy and the entire world, pretty much. As of before, we were just, more concentrated on what happened in these places, kind of not worry about other parts, okay, of the economy or other parts of the world or things like that, okay? Now, you pay for that. You don't get it for free. What do I mean by that? You're going to rely on strong structural assumptions, so about preferences, technology, and market behavior. Results can be sensitive to how migration, trade, and commuter friction are specified. Often require calibration using parameters taken from other studies, and sometimes it's coming from, I found it interesting, from one or two studies. They're all coming back to the parameter they're taken from there. But not always, it depends on the question. And there's limited ability to capture imperfect information, behavioral bias, or institution. So what I'm trying to say overall, this is a very promising avenue to deal with all of that, but that's come with a cost. Is it worth it? I personally think yes, because we are limited to what we can do with the other stuff, right, what we've done so far. But we need to be mindful there are some limitations, and we need to be very clear about how the different assumptions might affect the results of the paper. Okay? So it's kind of like this, I guess, one point to make here is that the other option is just not to think about it and not worry about it. I don't like it. I want to think about it. Is that perfect? No. But this is kind of one way forward, I think. And many people are doing great work. And I think that I already see that with time, really this kind of methodology improve dramatically. Now, I was curious whether we can teach you that in an hour or so. So I asked Sarah before. She was like, "There's no way you want to do that." But I just want to make the point to kind of just to introduce you to this point. If you're thinking about working on that, you're going to have to spend a lot of time reading a lot of paper in this literature and really understand how it works. Okay, and if you're interested in that, I can point you towards 4 or 5 seminal papers that I think can give you a very good understanding of how it works. Yeah, I think that's all I wanted to say. On a personal note, that was our last lecture. I'm not going to teach you lectures anymore. We're going to have seminars. Don't worry. Don't cry. But I had a great time, and I hope that you enjoyed it. Thank you so much for coming to 4 to 6, between 4 and 6 every week. And I see you on Wednesday. Okay? And yeah, thank you. And there is a career event, I think, which I'm not going to be in, but Stephen is running it, about consultancy. Yeah. All right.
Yeah. No way, no
What?
way. Like, I'm not getting up at 7:50.
Wait.
What,
You
to catch the
leave
bus?
at 7:15?
To cycle or to catch the bus?
7:15?
As in 7:15? You leave?
No
Bro,
way.
you're faster walking. Like, you're literally.
No, but I do the same thing. I leave around 7:20.
You're faster walking.
What?
Like
No,
then
no,
I'm
no,
not-
what?
7:15?
Oh, no, not to get here to, yeah, not to uni. But then I avoid the full buses. Or like the
No, but
buses that we
7:15
check.
is already full buses. 7 to 9
No,
is like